welcome back to Everyday Metallurgy. This is part 2 of an episode on hot work tool steel. Previously, we learned about general, what is tool steel, how is it manufactured, how is it heat treated, and how is it forged. But today we'll dive into some of the application for hot work tool steel. We'll dive into the properties of hot work tool steel, and we will talk about the defects that we sometimes see. Finally, we will go deeper into the future of tool steel. Have we finished, or are there still new things coming? And finally, we will talk about where you can learn more if tool steel is your area of interest. But enjoy this episode.
Ingolf, if we jump to the purpose of this podcast is called Everyday Metallurgy, and everyday is applications. Where is it used? Where are tools still used? If we look around in the world, can you give a short introduction to that?
Of course, yes. I share the presentation again, if you allow.
Yes, I do.
So tool steels are mainly used in 4 applications. That is, for example, die forging, and that is die casting. And in the next slide, I show you some examples. That is also extrusion, or since, let's say, 10, 15 years, also hot stamping. That means forming sheet metal, which is heated up to austenitization temperature and then shaped and quenched in water-cooled tools.
So, I saw that. I had a presentation with a guy making panels for cars. And he showed that when working with these very high-strength materials, steel that cars are made of today, you need to hot form it.
Yes.
Because it's just too hard to form when it's cold.
Yeah, that is true indeed. And you use this process of hardening to, first of all, use the benefit of applying thinner sheet metal, but you can compensate You can compensate the loss of strength that you would expect by increasing the strength with this hot stamping process. That means you harden the sheet metal and achieve extreme high strength values, much higher than traditionally cold shaped sheet metal parts. That contributes to safety of the passengers in the car, but also to weight reduction.
Exactly, yeah.
And here I have some examples which you every day use. At least when you use a car with a combustion engine, then you have a forged crankshaft, which you see.
I don't do that.
Sorry?
I don't do that.
Well, I used to recommend that everyone buying an electric vehicle should ask for a crankshaft to be given, just in case.
Yeah.
These crankshafts are usually forged, and then on the right side you see a die-cast engine block for a combustion engine. But of course, also in the electric vehicles, then you find the bodies for the electric motors, which are made by die casting of aluminum. Then various profiles are made, for example, of aluminum for so many purposes by extrusion. You see that in the lower figure. That is such a wide variety of profiles, from very fine profiles for air conditioning systems up to very large spacey profiles which are used in railway wagons. So the range of products made with the help of hot work tool steels is very wide. And you even find plastic molding applications where you find hot work tool steels as the tool material.
Yeah, I think we use it a lot at Syntex when we make metal injection molding.
Yes. Yes, you apply a high temperature and the tool must compensate or must withstand this high thermal load, and this requires hot work tool steel which does not lose the properties over a long lifetime.
Exactly, yeah. So if we look at these components, what is important? What properties are needed for the steel to survive? Because I could imagine an engine block like that made by die casting, you need to be able to make more than 5 in the tool.
Yeah, the usual lifetime of a die casting dies is more than 100,000 parts during the lifetime of such a die.
Yeah.
And nowadays they often aim for even higher numbers because these tools are very expensive. They can easily cost more than 100,000 euros. And in case of these giga casting dies, which you nowadays find more and more, that can be millions of euros. So the main properties that we face in the applications are listed here depending on the application. So in case that you run a forging shop with die forging operations, the tools are usually exposed to a high thermal load and mechanical load. And the compensating properties are, first of all, very high tempering resistance. That means resistance against undesired softening. Then it's also high temperature strength. That means that even at an increased temperature, the strength should not drop too much.
Yeah,
it will, of course, to a certain value, but it should be it should not drop too much. Toughness is always very important, especially if you look at the sudden mechanical loads that you see in a forging operation. It is understandable that toughness plays a high role. Due to the contact with a hot material that is forged, you have a thermal shock with each operation, and that must be compensated with a high thermal shock resistance. That is a property, not really one property, it is the that comes from the high thermal shock resistance depends on high temperature strength and toughness. So a good combination of these properties, high temperature strength and toughness, is leading to a good thermal shock resistance. In die casting, for example, aluminum, we shoot liquid aluminum nowadays with temperatures above 700 degrees into the steel die, into the mold of hot work tool steel. Yeah. And this mold is filled within fragments of a second. And even when you look at these large underbody structures, which you have in some cars today, then you shoot more than 120 kilograms of liquid aluminum within a fragment of a second into such a die. You can certainly imagine how sudden these thermal and mechanical loads come up.
Yeah. And don't you have wear on the die when at the inlet area, because velocity of the liquid must be pretty high?
It is. I heard a value that says velocity can be locally up to 70, 80 meters per second.
Wow.
That is really fast. Yeah, you need to fill the die very rapidly. Otherwise, you will start solidifying the aluminum before it is completely filled.
Yeah.
And so here again, we need good tempering resistance, high temperature strength, and toughness. And of course, with each shot, as we call it in die casting, we have a thermal shock. That comes, of course, from the contact with the liquid melt. And then after the solidification, they spray a liquid release agent or a lubricant on the die surface. And traditionally, that is still water-based lubrication, and that evaporates immediately and causes a high thermal shock on the surface, which after a while will lead to thermal shock cracks. Then there is written chemical reaction. We have the critical situation that liquid aluminum reacts with the steel. Aluminum has the ability to solve iron, and the lower the iron content in the aluminum alloy is, and the higher the temperature is, the more aggressive is the liquid aluminum to the steel. And so you can see later, after a while of casting, some washout situations in the die, so where really some steel has gone.
Okay, so it's not the aluminum that enters the steel surface. So like I know when you make galvanizing, you create an intermediate phase between the iron and the zinc. But here, do you also create an intermediate reaction between the iron surface in the tool and the liquid aluminum, or is the time just too short?
Yeah. And then the aluminum, which is not saturated with iron, wants to get the missing iron, and it takes it from the steel.
Okay.
This is a reaction that is hardly to compensate, from my experience, by the steel.
Yeah.
It can be controlled a little bit by thermal control of the process, or of course with coating of the dies. So in extrusion, we then press round bars of aluminum, of copper, or whatever, even steel. We press it through a die to hollow or massive shaped profile, as we have seen on the photo a few minutes ago. That is a long-lasting process. So the dies are usually, or the tools, the complete tools are long-term exposed to high thermal load and mechanical load. So we need to avoid softening. We need to provide a high strength to the die materials and to the other tool materials there. And of course, sometimes we need to have a good thermal conductivity to get rid of excessive heat in the die or in the so-called container where the billet which is extruded is contained. There we need to provide a thermal homogeneity, and that requires heating and cooling, and that of course also needs a certain thermal conductivity.
Yeah.
Yeah, in the application of hot stamping, we have again high thermal load with the contact of the sheet metal that is heated up to 900, 950 degrees. We have then, of course, a sudden and deformation, the high mechanical loads, and that again requires good tempering resistance and high temperature strength and toughness. And here we see very often and very fast abrasive wear. And to prevent that, we need to have high wear resistance.
And how do you do that? Is that by using some steel with primary carbides?
Usually we avoid primary carbides because these steels also need a good toughness. I will show later on a cut through such a tool, and I will show how close these cooling channels are below the surface. So in most cases, people think the higher we take the hardness, the better is the wear resistance. But that is only true to one aspect. Of course, with increasing hardness, you can improve the wear resistance to a certain level. But the problem is that you automatically reduce the toughness. And keep in mind that these tools for hot stamping are water cooled. They pump ice cold water with a temperature of 5 to 6 degrees through these tools. Yeah. And the cooling channels are only 5 to 6 millimeters below the working surface. So you can easily imagine what the temperature gradient between the cooling channel and the working surface of such a tool is. And that, of course, creates very high stresses. And they need to be compensated by good toughness. So then you better select a steel material with higher carbide content than a standard grade like 1.2343. Then maybe you use a steel with 7% chromium and a little higher carbon content. That still does not develop primary carbides, but it develops a high volume of secondary carbides and provides then sufficient wear resistance.
Ingolf, I have also seen some applications where properties like mirror shining surfaces, so polishability is important, and corrosion resistance is important. What is that for?
Mirror polishing is important if you use hot work tool steel in a plastic mold application, because nowadays when you look at packages, for example, for cosmetics, the requirements regarding the surface are extreme. But also for visible car parts, you need to polish the molds, the plastic molds, to mirror quality. Because the liquid plastic really copies the irregularities from the tool surface. And even if you have only like a needle stitch surface defect, like a needle stitch, the tool cannot be used anymore. It needs to be remachined, repolished. And plastics are also used nowadays in medicine, in medical apprentices, in medical appliances, where you have to provide certain optical qualities. And so there is the necessity for excellent polishability. That can only be achieved if you have an excellent cleanliness of the material. That means remelted material. Either ESR or vacuum arc remelted. Then you need to have a very homogeneous and fine-grained grain structure, because if you get coarse grain, you get easily the so-called orange peel structure. And that is not desired in plastic applications.
No.
So this is something where you need to where you need this high polishability. That is difficult to achieve. Hot work tool steels in plastic mold applications are usually used with a hardness of, let's say, around 50 to 52 Rockwell C. Whereas in die casting, the hardness of the tools is in the range of 45, 47 Rockwell C, depending on the steel and on the dimension and shape. But so the higher hardness of the steel tools makes it a little easier to give the steel a good polishing. But polishing is very often done manually, and it requires also a really experienced person to achieve this excellent surface quality.
And then corrosion. I remember there are some alloys that are extremely high in chromium, so it's like a mix of a tool steel and a stainless steel.
Yeah, most hot work tool steel have chromium content around 5%, more or less.
Yeah,
They
that's
have,
pretty low.
Yeah, and they are certainly not corrosion resistant.
No.
The problem is when you need to have a good corrosion resistance, you need to apply a high chromium level and also some molybdenum. These elements are also necessary for some high temperature properties, like the so-called secondary hardness for the precipitation of the secondary carbides, which are responsible for high temperature strength and tempering resistance. But the problem is, the more chromium or molybdenum you add to the steel, the lower will be the thermal conductivity. And thermal conductivity is very important, for example, to control the solidification in a die casting die.
Yeah.
It is also very important in the hot stamping industry because they want to work with a high rate and production rate. And let's say around 10 years ago, there came up a very intensive discussion about the importance of thermal conductivity. But you have to decide for either good mechanical properties or thermal properties like thermal conductivity. That is the problem usually.
Okay. So it's a trade-off.
It is, yes, indeed, indeed. But the corrosion resistance is getting more important, as I can show in one of the next slides here.
Now.
All right, here in this slide, we see in the lower left photo a segment which had been cut from a cracked hot stamping tool. And what we see here, this is the working surface here. And here we have the cooling channels which follow the geometry of the tool. And here we have a feeding water channel, and here we see a lot of corrosion.
Yeah,
and we also
brown.
see, sorry?
Yeah, it looks brown.
Yes. And later on we found that this crack which we have here had been caused by corrosion starting from the cooling channel. And this is the highly stressed area of the hot stamping tool. Here, the sheet metal flows over this corner, so we have a lot of stresses in this section. And this was probably a kind of stress-induced corrosion, and that corrosion crack grew into the direction of the working surface, and later on the water leaked out.
Yeah, it doesn't work.
Yes, and nowadays in die casting we have similar activities. We have local cooling with some cooling channels coming very close to the surface of the die, and the risk that water leaks out of the tool and can leak into the cavity of the die casting die is much higher, because then the contact with water and liquid aluminum might lead to explosion, and nobody wants to have that.
Yeah, that is a mess.
Yes, and so corrosion is an often neglected phenomenon, and the closer the cooling channels now are to the working surface, the higher is the risk. So
of the photos, that was the reaction of the aluminium dissolving the iron. Is that what we see there?
No, I don't have such a photo available, but what we see here is a different kind of effect that is abrasive wear in a die forging die. You see the traces where the material is really worn out. I hope it is visible here in the die casting die. We see a massive cracks here.
Wow. Yeah.
I hope it is visible.
Mm-hmm.
And then up here, this is a typical appearance of the so-called thermal fatigue cracks or thermal shock cracks. Here we made them visible in the magnetic particle test with ultraviolet light. So each green line shows a fine crack. And usually these cracks appear in a kind of a network as we see it here.
Yeah.
So the aluminum picks up that shape of these cracks, and you will find the traces of the cracks on the cast component. That is for many applications not a problem when you think of a gearbox or transmission housing, a clutch housing of a car. Nobody cares for visible traces of these cracks. But the problem is that these cracks grow into the steel and they might lead to particles breaking out or even total cracks going into the cooling channels.
Yeah.
And
how
nowadays,
big are they when the particles fall out? Is it a millimeter big or are we more micron level?
No, these cracks can go down to, let's say, 1 to 3 millimeters usually, and then they are getting critical because the aluminum flows into the cracks and it makes it difficult to demold the solidified part from the die.
Yeah.
The other thing is that nowadays we have also a lot of die cast components in the cars which have visible surfaces and aesthetic surfaces. That means the requirements are extremely high because nobody who buys a modern car wants to see traces of thermal shock cracks on the visible cast components.
Yeah.
And you also have mounting surfaces in these cast components. And if you then have a burr from as the trace of the crack on the casting, then mounting these parts into a car would be difficult.
Yeah. So if we look into the future, how do you see the evolution of hot work tool steels? Have everything been developed and you can go on your pension and be happy? Or
no, that would not only be boring. The thing is that I would say that as we still see a lot of development in the business of die casting, for example, with regards to larger components, we see increasing demands. We see also the economic pressure. So most of the well-known steel producers have in the last 25 years developed several special grades which have improved property profiles, for example, improved toughness, improved thermal shock resistance. Nowadays, there is also the importance to make these steels affordable. That means easily heat treatable, and also they should be available for a comparably low price. Of course, that is sometimes difficult to achieve, but if you consider that in Europe, for example, the price for the steel of a die casting die is perhaps 15% of the total die cost.
Yeah.
It will not really matter if this premium grade steel is a few euros more expensive compared to a standard grade. It will provide better properties, which provide a longer lifetime, less service in the die life, and certainly a more reliable production. But the price pressure is very high in these days, and so the casters need to fight for every single euro or penny a cent, and that means steel nowadays steels must provide good properties as well as reasonable prices. So there is still some development going on with regards to improved properties or adjusted properties. But of course, the standard grades still play a large role in the hot work business. My position or my feeling is that there has not been yet an end. There is still work going on, and I hope it will continue like that because the requirements will grow.
Yeah, and I could also imagine the 3D printing technology with the potential of making conformal cooling, where you can place very complex cooling channels just below the surface, as you talked about previously, could make a change in the speed of how fast you can solidify in both die casting and plastic injection molding.
Yes. Indeed, yes, the solidification rate is very important, for example, in die casting. At the position where the melt enters through a pipe into the die, they always keep a reservoir of liquid aluminum or magnesium from which they feed in case they have a shrinkage in the product.
Yeah.
So this reservoir has a much thicker cross-section and is the part which solidifies at least at the end of the process. And that means if you can increase that solidification, you get shorter cycle time again, and that helps to improve the economic aspects of die casting. And that is certainly the great advantage of this conformal cooling, where you can create structures of cooling channels which are unbelievable.
Yeah.
From my point of view, these additive manufacturing applications have their advantages, especially in these sections of a die casting die.
Yeah. So it's how big can you go with 3D printed structures? Have you seen? You said tool of, was it 60 ton for the biggest die casting?
What I have seen was the die made for the rear underbody of an electric vehicle. I don't tell the name, but each side of the die had a weight of approximately 60 tons. So the total die had a weight of around 100-120 tons. Of course, most of the die was made of ESR materials, and especially in the shaping area. Then there is also a frame around the inserts. But I think the 3D the inserts which could be made by 3D printing would be size of 1 or 2 fists of an adult person.
So still quite big.
That I would say is what I can imagine the reasonable size.
Yeah.
I might be wrong. I'm not so experienced with additive manufacturing.
No, but I'll bring this out to the audience, and if somebody out there are working with something this size, the fifth of a man, and is a grown-up man we're talking, then I would love to see examples of that. So please fill in with your comments if you are into that.
Yes, please.
Yeah. Ingolf, I think we have come to an end. Where could people learn more? Are there conferences? If you want to be a part of the tool steel community, where should I go?
It depends a little bit of whether you want to see it from the scientific point of view. as a material scientist. Then there is a series called Tooling Conferences, which had started, I think, in the 70s, originally set up by Böhler Oderholm, and then Thyssen Edelstahl, very strongly supported by the Bochum University, later on also Leoben University in Austria. So this series of conferences is obviously still going on, and there had been more than 10 of these conferences every, let's say, 3-4 years. They really are on a scientific level. If you want to see it more from the application level, there is a very good, it's very good to go to visit the Euroguss exhibition, which is every 2 years in January in Nürnberg, in Germany, in Nürnberg. Next one will be in January 2026. And that is a 3-day exhibition mainly concentrating on die casting. Then you have presentations there from steel producers, from casters, where you see a lot of really interesting and important developments with larger and larger cast products. That is a good place to visit. Also exhibitions on forging or the North American Die Casting Association, the NADCA conferences, which are usually held in September, October, are also very interesting to visit if you see the application from the scientific and application view. So there are several ways to step into that field of activity.
No excuses left.
Right.
Yeah. Ingolf, thank you very much. I really enjoyed it. And even though I have been working in the tool steel area previously, I learned a lot new today. So thank you for sharing.
It was a pleasure to talk to you, Peter, as a very old friend and colleague, and also to talk about the field that I have been working on for more or less 30-40 years now. And yeah, let's see what the viewers will see and what comments will be, and will be curious to find out what kind of comments will come and what kind of questions. I'm open to try to answer them.
Thank you very much.
My pleasure, Peter. Yeah. And good luck for your YouTube channel.
Thank you. See you.
See you.
Thank you very much for watching this part 2 of the episode on tool steel. We have learned a lot about what tool steel is, how is it manufactured, but one of the things that we didn't mention, and Ingolf, he passed over, was the powder metallurgy route. And next episode, that will in fact focus on that. I have invited a top specialist in hot isostatic pressing, where the powder metal tool steel, they are very often made in a hip cycles. But we'll not only dive into tool steel, we'll look into hip in general, because hot isostatic press is exploding as a technology. Everybody are using it. Casters, 3D printing technologies, of course the powder people. So tune in, subscribe to this channel, and stay ready for next episode on hot isostatic pressing.